So, good morning, everyone. And this is Work Power Energy, lecture number 25. In the previous lectures, what we were discussing, I think we were discussing concepts about uniform circular motion. We had discussed what is uniform circular motion, and we had seen that if omega, which is the angular velocity, if it is constant, then the motion is known as uniform circular motion. In case of a uniform circular motion, the average angular velocity, whatever time interval you take, will always be equal to instantaneous angular velocity. In case of a uniform circular motion, we had also seen that it will always complete one circle in a fixed time, one revolution in a fixed time. That fixed time is known as the time period of uniform circular motion and is denoted by the letter T. I hope remember the letter T, capital T, time period. At the same time, if you are talking about the inverse of time period 1 by T, that will tell us how many revolutions, oscillations, SHMA oscillation we call it, how many revolutions or oscillations this body is going to take in 1 second. That is known as the frequency of uniform circular motion, and the relation between frequency and time period, which I am now marking in pink, is very simple. Frequency is 1 by capital T. I hope we all recollect this. The SI unit of frequency, as we had seen, is hertz, which is 1 by second. The dimension becomes 1 by T, or T raised to the power minus 1. Omega also becomes 2 pi by T, and that is equal to 2 pi f. Omega is angle multiplied by frequency. So in some cases, especially in AC and simple harmonic motion, we will be calling omega by angular frequency. Remember, angular velocity for uniform circular motion, or for that matter rotation, we'll call it angular velocity. But in case of alternating current AC and SHM, we would be calling it probably by angular frequency. Then we had seen some small formulae. If it is taking n revolutions per second, n becomes frequency. N revolutions in t seconds, n by t becomes your frequency. If it is taking n capital N revolution in 1 minute, then it becomes your frequency becomes capital N by 60, which is right now on your screens. It was pretty damn simple. We had also seen in the previous class, and if I can recollect it, the other concept, the concept of acceleration. If omega is not constant, and I told you if omega is not constant, then what happens? If omega is not constant, we have acceleration. And in this case, the acceleration is known as angular acceleration, denoted by the letter alpha. Angular acceleration denoted by the letter alpha. Again, we have two types of angular acceleration: average angular acceleration and instantaneous angular acceleration. Average angular acceleration is total change in angular velocity divided by total time, omega 2 vector minus omega 1 vector divided by total time. That is my average acceleration. It is average angular acceleration. It is also a vector quantity. Instantaneous angular acceleration is also a vector quantity, that is d omega by dt. Average angular velocity is a scalar, but instantaneous angular velocity is a vector. I hope you all recollect this. Can I have some raised hand that we understand this? Can I have some raised hand that we understand this? Okay, so we understand this. What I'm going to do now is just memorize or write all these in one place, all this in one place, so that it becomes easier for you to recollect it, easier for you to recollect all these formulae. And here it comes. I think I have shared the wrong thing. Let me just okay, I hope it is visible to all of you. Now, let us recollect everything that we have discussed so far. The first thing is angular position. Angular position is given by the angle theta, which is going to tell us where the particle is. Angular position theta, where the particle is. This is a scalar quantity. The SI unit, I will write everything if you want to. It is a scalar quantity. The SI unit is radians. The dimension is, it is dimensionless. And what else I was saying? Yep, it is a scalar quantity. Do we understand this? Can I have some raised hand that we understand this? Angular position is the first thing, theta, that we have discussed. The first thing. Number two. What is number two? Anyone? Any idea what is number two? Angular position was the first thing that we discussed. What was the next thing that we discussed? Anyone? After angular position, what was the next thing that we discussed? No one knows it? What was the second thing after angular position that we discussed? Abhiram, Neha, Tarun, Vasant, do we recollect this? What is the second thing, second term that we discussed? Don't remember it? Okay, then I'll give you 2 minutes, 5 minutes to go through. I think you are not going through the, you are not studying at home. I mean, if you don't remember what is the next thing that we discussed, that is quite a surprise for me. Anyways, I'll give you 2 minutes. Go back. I hope you are making notes. Look at your notes and tell me what is the next thing. I'll give you 5 minutes to revise. Okay. So revise and tell me what is the next thing that we discussed. So I hope that you have gone through this, everyone, and we have studied angular position. What was the second term that we studied? The second term that we studied was angular displacement. If I am correct, angular displacement, that is denoted by delta theta. Change in angular position, delta theta, that was equal to final angular position theta 2 minus initial angular position theta 1. The SI unit was radians, dimensionless. What about scalar and vector? D theta, if I had d theta, that was a vector quantity, small change in position, angular position is vector, lekin a large change in position is a scalar. Do we remember this? Can I have some raised hand that we remember this, sir? Angular displacement was the next thing that we had discussed. Angular position, angular displacement. What was the third term that we had discussed after angular displacement? Will anyone tell me that? Mia says angular acceleration. Nia, that is not correct. Still not revised. Not a good thing. Angular velocity is what we had discussed. We had discussed two types of angular velocity. The first one was average angular velocity. Average angular velocity was denoted by this dabba and omega. Dabba and omega. Dabba meaning average, omega meaning angular velocity. That was total angular displacement divided by total time. So it became theta 2 minus theta 1 divided by total time t. What type of quantity it was? It was it is definitely a scalar quantity. The SI unit, theta is radian, time is seconds. So it is radians per second. Do we remember this? SI unit is radian per second. And the dimension is 1 by t or t raised to the power of minus 1. Can I have some raise hand that we understand this? Yes, sir, we have an understanding of this. Okay, great. Average angular velocity. What was the fourth thing that we had done? The fourth term that we have studied was instantaneous angular velocity. Yes, Nia, now you are getting in the groove. Instantaneous angular velocity at this instant. Angular velocity at this instant. Angular velocity at this instant. It was denoted by vector, omega vector, and it was dt, the theta vector by dt, the derivative of small change in angular position or small angular position divided by small time. That was my instantaneous angular velocity, and this is definitely a vector. Why it is a vector? For the simple reason that in green d theta is a vector, small change d theta is a vector. It is d theta by dt, which is omega, and hence omega also becomes a vector. Do we understand this? Can I have some raised hand that this is vector because d theta, the green one, the green Hulk is a vector. The upper wala one, which is the pink Hulk, is a scalar. Why it is a scalar? Because d theta, small change in angular velocity, a small change, large change in angular displacement, that is a scalar, and hence we have, oops, wrong color, and hence we have this one as a scalar. Can I have some raise hand that we understand the reason of both being scalars and vectors? Okay. We talked about vectors in circular motion or in rotational motion, and I told you these vectors are a different type of vectors. They are known as axial vectors. Their direction is given in terms of axis of rotation. Axis of rotation. If something is rotating on positive x-axis, this is how it rotates. You hold the positive x-axis in your right hand with your thumb pointing in the direction of that axis and your fingers curling around. That will give you the direction of rotation. So this type, it is rotating on positive x. This is how things will rotate on negative x. This is how things rotate on positive y. This is how things rotate on negative y. Do we understand this? All these are axial vectors and their direction is given by RHT, the right hand thumb rule. Can I have some raise hand that we understand this? Right hand thumb rule, RHT. This was instantaneous angular velocity. Then the next things that we discussed was uniform circular motion. Yes, we discussed angular acceleration as well. So let us first also discuss about UCM. If omega is constant, then the motion is known as UCM. In that case, average angular velocity will be equal to magnitude wise instantaneous angular velocity. Instantaneous angular velocity, and we had seen frequency is equal to 1 by t. Angular velocity omega is 2. Omega angular velocity is 2 pi by t, or it is equal to 2 pi into f. Do we understand this? Do we remember this? If omega is constant, it is known as UCM. Frequency is 1 by t, omega is 2 pi by t. That was when omega was constant. Again, giving you time to note this down, because I want everything that you do at one place, so that what? It becomes easier for you to revise them when you want to. I'll give you a minute to note it down. I hope you have noted it down. Well, the next thing that we discuss, the last thing of yesterday's class, was if omega is not constant, then what happens? What changes omega? Angular acceleration. We had discussed two types of angular acceleration. The first one was average angular acceleration. Yes, Nia, that is correct. Average angular acceleration. Oh, why I'm writing omega? I should write alpha. Alpha vector, it is a vector in a dabba. Dabba means average. That will be equal to final angular velocity omega 2 minus oh, I should write it in that way first. Let me just write it that way. It is total change in angular velocity delta omega divided by delta t. So that will become omega 2 vector minus omega 1 vector divided by t. Now since omega 1, omega 2 all are vectors, this gentleman definitely becomes a vector. What type of vector it becomes? It also becomes an axial vector. You all know this. That was average angular acceleration. The last thing that we discussed in yesterday's class. Yes, Nia, now you are on the point, on the dot. Instantaneous angular acceleration. This is what I want, beta. Every one of you should be on your feet. Whenever I ask something, the answer should come first before my question. Instantaneous angular acceleration, alpha vector, that becomes d omega vector, small change in angular velocity divided by dt. This is also a vector. This is also an axial vector. The SI unit is radians per second square. The dimension is 1 by t square or t raised to the power of -2. That is all we had discussed in the previous class. Now, what we are going to do is solve 2 or 3 problems based on this so that the definition of these terms they get into our head. So we will now solve a question and see how we can apply these things on to a question. Now remember, before solving any question, we must also remember that whenever we are solving any question in circular motion or rotation, see, this is an axis on which things can rotate. Now there can be infinite number of axes on which bodies can rotate or bodies can perform circular motion. But we are not going to deal with other axes. For example, if one body, the question, a body is moving in a circular path on this axis, it will only be moving along this axis. It will not rotate along this axis because then there will be 2 axes and the problem becomes very complicated, which is out of the purview of this course. That question doesn't come. Now, the question that are going to come will only be based on one axis. So basically, you can think it of as motion in one dimension. The type of circular motion or rotation that we are going to do is just like motion in one dimension. Things are only going to move either forward or backward. Forward or backward. They will not turn. They will not take a turn. Now, in circular motion, what it means by they will not take a turn, we're talking about vectors here, axial vectors here. So in circular motion, what do we mean by they are moving in a straight line? They will only rotate if they are rotating on this axis, positive y. They will only rotate like this, or they will only rotate like this. So they will only rotate on one axis. They will only rotate on one axis. If they are rotating on y-axis, they will either rotate on plus y or they will rotate on minus y. If they are rotating on x-axis, they will either rotate on positive x-axis or they will rotate on negative x-axis. If they are rotating on positive z-axis, they will either rotate on positive z-axis or they will rotate on negative z-axis. Am I clear? Can I have some raised hand that we understand this? Raised hand gives me a lot of confidence that we have understood this. So, to solve any question in circular motion, we should have sign convention. We should have sign convention. Now, the sign convention that we use in 1D motion or 2D motion was very simple. Same sign convention we are going to use here. If something was moving along positive x, it was positive. Negative x, it was negative. positive y, positive, negative y, negative, positive z, positive, negative z, negative. The same thing we are going to do here, but somehow a bit different, because you must understand that oops, what is this? Okay, this is good. Okay, so now if I take a circular motion, a circular path, which is like this, and if I imagine something moving on this circular path, now these are the type of question that will come to you, so we'll only concentrate on this one. Now, in this circle, the blue circle, either the thing will move like this or rotate like this, or if I make the green circle, there are two circles that I have made, so it will move like this or it will move like this. As you can see, both are opposite. Do we understand this? Can I have some raise hand that we understand this? The blue circle is like this, the green circle is like this. That is the only way things are going to rotate for us. Now, if you look at here, this is the direction of rotation. This is the direction of rotation. Let me not write omega. This is the direction of rotation. Now, this direction of rotation, as you can see, is anti-clockwise. ACW. The clock rotates like this. It is rotating ulta. This is anti-clockwise. Now, if I look at the axis of this anti-clockwise direction, it is actually positive z-axis, and hence the sign convention tells us that if something is rotating anti-clockwise, we are going to treat it as positive. They are vectors, so they must have direction. These are axial vectors. They have direction in terms of axis. If something is rotating like this anti-clockwise, it is basically moving or rotating on positive z-axis, and hence anti-clockwise rotation is always taken as positive. We have discussed this in the very first class when I told you about the sign conventions of angles, and I told you anti-clockwise angles are positive and clockwise angles are taken as negative. Do we remember that? Why it was taken in that way? Because of this axial vectors. Anti-clockwise means positive z-axis and clockwise means negative z-axis. Do we understand this? Can I have some raise hand that we understand this? So this blue one is positive, and this green one, if you look at this green one, the green one is rotating like this. It is rotating CW. CW means clockwise, and that would be taken as negative. That would be taken as negative. So this is a sign convention for circular motion or for rotational motion, and we will follow this sign convention always. Shall we move ahead? Okay, so now let us try to solve a question. Okay, let us solve this question. Question number 1. body is moving in a circular path of radius r. It rotates by 30 degrees. It rotates by 30 degrees in 5 seconds anti-clockwise. Find angular displacement and average angular velocity. Is the question clear to all of you? Is the question clear to all of you? Okay. I'll give you 2 minutes to solve this. I hope you have done this, everyone. Can I have some answers? What is the angular displacement? It is moving in anti-clockwise direction. So the angular displacement would be 30 degrees. You cannot give the answer in degrees. You have to get the answer in radians. How much is 30 degrees in radians? You must know this. 180 degrees is pi radians. So 30 degrees would be pi by 6 radians. Am I clear? Pi by 6 radians. Do we all understand this? Okay. Then what is average angular velocity? What is average angular velocity? Average angular velocity is total angular displacement divided by total time. Total angular displacement is pi by 6. Total time is 5 seconds. So I divide pi by 6 by 5 seconds. Answer would be pi by 30 radians per second. Do we understand this? Everyone got this answer? Can I have some raised hands? Well done, bacha. If you have done this, well done. I will now move on to the next question. Question number 2. I hope everyone has noted this down. That takes us to question number 2. What is question number 2? A car is moving in uniform circular motion completing 120 revolutions in 2 minutes. Find number 1 time period, number 2 frequency, and number 3 omega. Omega is the angular velocity. This is performing UCM, so angular velocity omega will remain constant. All of us know this. I will give you a minute to win it, a minute to solve it, and then we shall discuss the solution for this one. Have we done the problem? I'll give you one more minute. Let us now see the solution of this thing. So basically what is given here is the car is moving 120 revolutions in 2 minutes. 120 revolutions in 2 minutes. Let us first find out the frequency. Frequency is number of revolutions in 1 second. I have also given you the formula for this. Number of revolutions in 1 second. It is taking 120 revolutions in 2 minutes. 2 minutes is how many seconds? 2 minutes is 120 seconds. So basically it is taking 120 revolutions in 120 seconds So how many revolution it will take in 1 second? So frequency become 1 hertz. Do we understand this? Can I have some raise hand that we understand this? Frequency becomes 1 hertz. Time period is inverse of frequency, that is 1 by f. So time period becomes 1 second. Do we understand this? Can I have some raise hand that we understand this? Omega, which is angular frequency or angular velocity, is 2 pi by t or 2 pi into f. No matter how you do it, you will again get the same answer, 2 pi rads per sec. Are we all on the same page and we understand how this question is done? Can I have some raise hand that we understand this, sir? Raise hands will give me more confidence. Okay, I'll give you a minute to note down this question. And your time starts now. That takes us to the next question, and the next question looks like this. The question is on your screens right now. Very simple question. A body is performing circular motion. Its angular velocity is changing. At some point in time, it is 5 radians per second, and the direction is clockwise. So from 5 radians per second clockwise, it changes to 10 radians per second anti-clockwise in 6 seconds. So previously it was 5 radians per second clockwise. Now it is 10 radians per second anti-clockwise. The time it has taken is 6 seconds. You have to tell me what is the average angular acceleration. I have written omega as vector because omega is a vector. I have written average angular acceleration as a vector because it is also a vector. I'll give you 2 minutes to solve this one. Your time starts now. Let me give you the solution of this one. The initial angular velocity in green, the initial angular velocity was 5 radians per second and it was clockwise. Green one, 5 radians per second clockwise. So I'll write it as omega 1. Omega 1 will be 5 radians per second. So it is 5 and it is clockwise. So I write it as minus 5 according to my sign convention. We all agree on this? Can I have some raised hand that we agree on this? Initial angular velocity, the green one, is minus 5 radians per second. The final angular velocity, as you can see, is in pink. It is 10 radians per second. So I'll write omega 2, which is the final velocity. It is anti-clockwise, so it will be plus 10 radians per second. This is the pink one. Do we understand this? Can I have some raised hands that we understand this? No one understands this? Great. Yes, Nia, that is the right answer. Now I just put the formula for average angular acceleration with the sign convention. Average angular acceleration is omega 2 minus omega 1 divided by the total time. Omega 2 is plus 10 minus 5 divided by 6. So answer will be plus 15 by 6 rads per second squared. That is the average angular acceleration, and that was the answer that I was looking for. Everyone understood this question? Can I have some raise hand that we got this up? Just applying this simple formula with sign convention, had you should have got this answer. We finish our today's class here. In today's class, we have discussed the basics of circular motion and we have seen 2 or 3 problems based on those basics. In the next class, we would be dealing with The equations of circular motion that would be dealt with in the next class. Till then, I hope you keep on revising and you keep on studying. Stay safe, stay at home. I'll see you in the next class. Bye bye.